Okay, so after a frustrating morning, I think now it's afternoon. Yeah, I've started this at about 7 o'clock this morning. So 5 hours I've been battling this. Hopefully now it works. Week 9, it's not 9A or 9B because it's probably the only lecture we'll have this week. Maybe I'll be able to squeeze in a second now that I think I might have this figured out. We're going to talk about the first of the two types of bearings we're going to look at, and those are called journal bearings. As usual, we'll start with a little housekeeping. Um, so the office hours on Monday morning I thought went pretty well actually, and it's so something's going well. There are, I think, more people at quote unquote. Hold on, let's see if I can get this to work. Um, there are more people at office hours this Monday morning than there had been in previous office hours. So I think maybe that's a success. And I especially appreciated the fact that you would kind of chime in and help each other out. Hey, try turning your microphone off, or do this, or try this setting, or go into here and change this. Um, I thought it was pretty cool. Everybody kind of coming together and making things work. So I appreciate that. All right. Um, so the other thing, quiz. I think most people did pretty well. Uh-oh, this is going to be a problem again. I can tell already. Um, Most people did pretty well on the quiz. It looked pretty good, so we're back at Penn here. Um, the part of the reason I had um, the practice quiz was to give you some sense of how long it would take you to upload, scan and upload. And there were some last minute submission glitches. I got a lot of screenshots saying, "Well, I tried to submit it at 10:54 and it didn't work." Well, that's why you don't wait till the last minute. Literally, many of you waited till the last minute. Now, I'll be flexible. I gave you some extra time, and there are going to be glitches, so I'm going to be flexible. I want you guys to learn first and foremost. But in general, as engineers, don't plan on things going right. That's just, as an engineer, be conservative, be cautious, leave room for mistakes to happen. Okay, anyway, so a bearing overview. What is a bearing? A bearing is some sort of device that allows two parts to move independently of each other, right? So some of you might be into skateboarding or longboarding or whatever it is you kids call it now. But here's a set of bearings. I bought this whole stack of bearings on Amazon for $10. So this is just a little ball bearing. This is very similar to what you'll use on your project. So I can kind of pinch it in the middle here, and then spin the outside, much like the little widget spinner or whatever those things are. Different kinds of bearings, right? But these are ball bearings, probably what you're more familiar with. But to the first one we're going to talk about today is journal bearings. So just to make a couple notes on here, let's see if I can get that to work again. So these are, like Teflon or bronze. Teflon should be capitalized, I guess, or bronze also is a good, nice slippery bearing material. These are typically oil or air. The bearings in your hard drive are actually, it's a journal bearing, but it's actually air is the working fluid. And your hard disk drive, although most people now don't have disk drives, they have solid state drives. And then finally, on your quiz, you're going to use ball bearings, or on your project, and on your quiz for that matter, on your project. And then, those are all rolling element bearings. Here's some more pictures of what these bearings look like. All right, these are the ones I just showed you. These are ball bearings. These are this one here happens to be a tapered roller. Tapered roller bearing. And then here we have a journal bearing. Okay, so what this is, for the gearheads in the group, you'll know what this is. If you're not a gearhead, this is a crankshaft. It's part of the engine. This is kind of the guts of the engine. So remember in thermodynamics, we had some sort of piston cylinder device, that had something up here, and then this thing goes up and down. And as this connecting rod goes up and down, it also gets forced to go in a circle. And this is what we call the journal, or the shaft. And then this is the housing here, right? And so this part sits down in this part, there's nothing that rolls in there. It's just oil that separates these from wearing each other down, right? It reduces friction and it reduces wear. All right, so here's another picture of that. This is the piston cylinder device up here that goes up and down, and that's connected somehow. And then this goes up and down, and then there's these bearings here. Here's a cartoon version of what a roller ball bearing looks like. The family tree of bearings are really, there's two big types. There's the rolling element here, and then there's ball bearings. There's deep groove, angular, contact, filling notch, thrust, all these different bearings. But this is kind of it. So today we're going to talk mostly about hydrodynamic, but we'll talk a little bit about the self-lubricating. And by self-lubricating, it just means that these rub on each other directly, and they will wear down, and we'll talk about that briefly too. Okay, so speaking of self-lubricating, these are things, so they have higher friction, right, because there's nothing that rolls, there's no lubricant, right, so there's higher friction, but they're cheap, right, and they're very small. So for instance, if you were to go to the hardware store and buy some pulleys, so hardware store, caliber stuff, or quality stuff. Hardware stores, I noticed, are considered essential stores in this time of house arrest. They're also very small, right, because there's not much needs to be in there. They work over wide spans. The key thing here is that it's wear, right? Eventually these things wear down. When you just have two materials rubbing on each other, eventually they'll wear down. So Teflon is a typical polymer used for these things, and then bronze is one of the most composite, or one of the most typical metals. And sintered just means it started as a powder, and it got compacted and heated to make it into a solid. And so there's different coefficients of friction. So you notice that's on the order of 0.05. Which is pretty low as far as two materials sliding across each other, but still you'll see that's pretty high relative to other coefficients of friction. All right. Wear. All right. When we're using two materials just sliding across each other, they're going to wear down, right? And so what we're interested in is how much material are we losing, and that will be in millimeters cubed. All right. And then, so how does it wear down? Well, the harder it is, the less it'll wear. So this is hardness. And the units on hardness are funny, but typically there's something on the order of megapascals, right? Is what's going when we do these different hardness tests. This is a material property. K is called a wear factor here, and that's a material property. And that's also dimensionless, all right? So whereas we have 1 over the hardness here. This is the force with which we push down on things, so that's simply newtons. The velocity, how fast these two materials slide against each other, right, it certainly would affect the wear. So that we'll treat that in millimeters per second. And of course, over time, material wears down, right? So that is in seconds. Okay, so this all works out. We could plug all these things in here. We'd see that the seconds cancel with seconds. So this is actually millimeters squared per newton, right? Because it's on the bottom, so the newtons cancel out down here, and then we wind up with another millimeters squared. So we get the wear is in millimeters cubed. All right, now one interesting thing I want to point out about this is that where's the area, right? The area doesn't show up here at all. Area doesn't matter, right? Well, not really. This gives me the volume of material that's wearing away, right? And the volume of material is a function of the force, the velocity, and how long, right? So I could have a small surface that wears down fast, right? but that's equal to a large area that wears down fast. Because ultimately, what I'm interested in is how long does that surface, when does the thickness go away, right? And the thickness is the area times the thickness. The volume is the area times the thickness, and so that's we get the volume. So we could look at that as a volumetric change there. All right. Okay, so that's for many of you, your senior design projects, if we ever make it back to college, will result in that. Oh yeah, one more thing too here. I should mention something about this. There's a limiting PV, right? And that's a pressure times velocity. And a lot of these are limited by, so if we use these nylons, like here's nylon plus some Teflon and reinforced with some glass, blah, blah, blah. There's a limiting pressure times the velocity. I'm not sure what the units are in this one. I think this is in imperial units. But heat becomes a problem, right? If I just take nylon, straight up nylon, number 6 nylon, and put a lot of pressure on it, it moves really fast, it'll start to overheat, either burn or melt or wear away a lot faster. So there are limits in pressure and velocity for all these materials. Okay, anyway. So most of the work we're going to do today is going to be on these hydrodynamic bearings or journal bearings. All right. So at rest, when it's not moving, right? Say I've got some load that's on the bearing here. So this is remember, this is the shaft. And then this is called the housing. Right. So this thing eventually, so right now it's not moving. So it just squeezes all the oil up here like this. All the oil just goes up here. And we have metal on metal. Metal on metal there. All right, so not moving, it just sits there, okay? Now, as soon as I start moving, right, what happens? So this thing is moving here, this thing's not moving. So remember in fluid mechanics, we called this Couette flow, right? It's a shear-driven flow. But there's this heavy weight here, so there's a high pressure here. So, boy, this could begin to look like a fluids problem. Where I have shear driving the flow this way, pressure pushing the fluid back this way, and which wins, right? That's the whole point of Navier-Stokes, it's a balance between pressure forces, shear forces, gravitational forces, etc. And so when it first starts to move, there will be no slip here, and it's going to drive some amount of oil down into here. Maybe not enough to lift this thing completely, but enough so we can start to get some boundary lubrication, right? And then once I get up to speed over here on the far right, the shear driving the fluid down into here, right? So no slip, it's got to be no slip. But what it's really, really, really heavy, it's still no slip. And if it's no slip, the mass has to get transported down here, which means I'm going to have some film. Right, and we call this the minimum film thickness down here. Oil will fill this gap, lift this thing up, and then this is no longer riding metal on metal, it's riding metal on oil, right? And so that's how the journal or a hydrodynamic bearing works. So pros and cons of this. They're great for high-speed applications. Like I said, your hard disk drive in older computers rides on an air bearing because it has to be very small and has to spin very fast. It can take really high shock loads. So if I go back to this picture here, if I push down on this really fast, right, in order to accelerate oil out this way, enormous pressures in order to squeeze that oil through there. I'm not sure if we did a problem like that in fluids last semester. That's good. And there's never any surface contact, right? It's metal on oil, so there's no long-term surface damage, right? Disadvantage when we first start up, like this here, right, it's pretty high friction because it does start out metal on metal. There are ways to get around that using a hydrostatic system to pump oil in from the bottom. But for low speed applications, it doesn't work great. Okay. This picture here gives us a little better picture here. So here's the journal or the shaft, this rotates in here. And then This is the housing. So the clearance, right, and that's represented with the letter C often, is the little gap of oil when this thing is sitting at equilibrium. All right, so that's the clearance in there. And then this is, we call that the radius of the shaft, right? R, right? We call that the radius. Of course, it's the radius. All right. Now let's look at these lubricating regimes again. So this is no rotation, right? We have metal on metal, and what's actually happening at the microscopic level, these little imperfections are grinding against each other, right? Then we get into the mixed film regime, right? Low speeds. And there's a thin film here. For the most part, they're not touching, but a high spot versus a high spot, they're going to impact here. And I'll still have somewhere over the rainbow. And then finally, at speed, we will get the full hydrodynamic effect, full Reynolds lubrication in there, so the metal doesn't touch the metal at all. It's all filled with oil. Okay, so those are the three things. If we look at the relationship here, right, the coefficient is 0.05, right, which makes sense because that's about what two metals sliding across each other are, right? But then we get mixed film. It's mostly oil supporting it. It drops down to 4/1000ths, right? So much, much smaller here. And then once we get the full oil film, the full hydrodynamic lubrication, we get very, very low frictions. All right, so that's good. Okay, so how does this look? Look at this. We have, I love this thing down here. That is a non-dimensional number, right? Let's take a look at mu n over p, right? So mu, I remember that from fluids, is in stress time, Pascal seconds. N is the speed at which this thing is spinning, right? So that's radians per second. Remember, radians are actually dimensionless. And then what do I have down here is the pressure, right? So pressure is the total load divided by the projected area, which is d, let's call it L. So the full diameter here, and then L is how long. Let's go. So let's call this D, and this is L, right? So this is the projected area, right? And so I know that'll be in pascals, and sweet, look at this, pascals go away, cancel, seconds go away. So I've got some dimensionless number here, right? This is great. And then I have friction factor, another dimensionless one here. So this little plot here could work for any bearings, any oils, any diameters, any radiuses, any speeds, whatever, right? And this is a very universal plot. So what happens if I said, well, let's say oil stays constant viscosity, say the load stays the same all the time, so just N is changing. So I could say this is example N equals 0, and then N equals fast over here. Right. At 0 speed, metal on metal, a lot of friction, and I start to introduce some oil to the interface. The friction drops. But then as I go faster and faster and faster and faster and faster, right, I'm shearing that oil harder and harder and harder and harder. So this is increasing viscous shear. S-H-E-A-R. Increasing viscous shear in this regime here, right? So this is the sweet spot where I can really minimize how this works. Okay, so let's take a look at a simplified example first. So this is really just to kind of make maybe a link between the two. So this is our classic Couette flow, where the key dimensions are h, right, the height of the film, and then this is the velocity profile here. This is big U. This is very, very familiar. We've seen all this stuff before. in fluids class. I think most of you have taken fluids. I'm not sure if the BSCs take fluids or not. And then so, the viscosity just winds up being the um, the shear divided by the velocity gradient, and that's how we get stress time. And then so it's the force or the area, shear, velocity gradient here. So this is shear, and this is velocity gradient. Okay, the velocity gradient there, right? And if we zoom in here, right, this thing is rotating, this thing's not. Boy, it looks a lot like this, right? Except if this is so thin, if we assume this is very thin, right, we can say it's basically flat, right? So we can do this in Cartesian coordinates. So let's do that. We know that the total area of this thing is the length of the bearing, right, times the circumference. So the total area is 2 pi RL, right? U, right, is the velocity of the upper plate in this case, right? So this is U here. Where'd my U go? Here, U. And so that's 2 pi R times the speed, right? So this is actually in meters per second, right? And then H, the height of our film, is actually C. That's the clearance. That's the difference between the outer radius and the inner radius, right? And that's C, right? And then so we can get all that stuff. We can rearrange all this, right, to get the force. If I want to get the torque, right, I just multiply the force times the radius, and then I can get all this stuff. So I can say at any given speed, viscosity of the oil, the clearance ratio, the radii, the length, 4 pi, the constants, I can figure out how much torque is lost just by shearing the oil that's in there, right? And then the friction then becomes the total friction between the shaft and the journal and the housing, right? The friction between these two things becomes a function of some important things. So these are constants, right? That's just math, right? But then this thing here, right? This is dimensionless. That is, mu n over p is a dimensionless number, and r over c, that's the radius over the clearance, or the clearance ratio, right? That's another dimensionless thing here, right? R over c. That's also dimensionless. So whenever I see that the friction is what I'm really interested in, is a function of a bunch of dimensionless stuff, man, then we can do some interesting things with that. All right, but we made some serious assumptions here. These assumptions being that it's perfectly centered, right? The oil film does not support any load, right? There's no load on it. We're just simply shearing the oil. There's no lubricant flow in this direction, up and down, right? And then it's lightly loaded, right? So oil film does not support load, and lightly loaded, I guess, what's that all about, right? That doesn't make any sense. Anyway, so this is really just ignoring the weight of, ignoring the weight of the ice skater or whatever this is. But now if we want to make this a little more interesting, I'm going to say, okay, now I have some load, and this is rotating. It starts out with a really big film here, and the film gets smaller and smaller and smaller and smaller. Now I've got pressure working against shear, right? And when I have pressure working against shear, and then some things might be accelerating in there, wow, then this becomes the whole Navier-Stokes equation. And here's what it looks like. I've got the derivative in the x direction, so this x is the tangential direction here. Let's take a look at that. So this is the x direction, and then the z is the axial direction, so z is in and out of the page, right? So if I drew this, so this is y, this is x, and then z comes out of the page, right? Now, this is really, really hard, right? We'd have to solve this numerically. We wouldn't be able to solve that analytically, but we can make a couple assumptions, right? What if I have a very long bearing, right? So it doesn't look like this little skateboard bearing I showed you. It's something really, really long. So like a toilet paper tube or a paper towel tube or something like that. Then I could say, well, if it's really, really long, there's nothing changing in the z direction. Nothing changes in the axial direction. This isn't pipe flow. This is just circumferential flow. So I can get rid of this. And then I just have the x terms, right? This is integrable, right? I can deal with this, right? I think it works out to be separable, actually. And then if I have really short bearing, like the skateboard bearings, right, then I could say all the action's going in the z direction, and there's not much flow in the x direction. And so then it becomes this, right? And so I can simplify these two. In reality, the modern bearings are typically just a little bit longer than this, but not this long, right? Okay, so here is another combination of these two dimensionless variables, the clearance ratio, R over C squared, and then this other mu n over P, right? This is also dimensionless. We combine these and we call these the Sommerfeld number, right? And so any bearings that have the same Sommerfeld number will behave very much the same, right? And we have to go through and solve all this stuff, right? But if we rearrange this such that the Sommerfeld number pops out, we can count on people before us, Raimondi and Boyd, that can figure all this stuff out for us, all right? And so here's what it looks like. First of all, I get the Sommerfeld number of the bearing, right? And the Sommerfeld number is a function of the viscosity, the speed, the pressure, right? That stuff. And then R and C, the radius. So these are all physical parameters that I know. Parameters I know, okay? And then I can go from here and then go up and then get some minimum film thickness, right? I want to make sure that my H0 is at least as thick, probably a few times thicker than the roughness of my material, right? And so this gets non-dimensionalized by the clearance. And so I can, I don't want to go, much thinner than this because then it, won't work. So I want to stay in this white range here, right? And so I don't think actually you're going to have a homework related to this. The homework will be like this, where I can take the physical parameters of my bearing, combine them into this dimensionless number, and let's say I get this one here. Let's just say it's 1 for the sake of argument. And so I'm going to go up here and I say, well, what's the L over D of my bearing? How long or short is my bearing? Is it a paper towel tube or like a skateboard bearing? So I go to here, and then from there I go back over here. And then I can figure out what my friction coefficient is, right? Now, this is given an RCF. I'm not sure why the RC is in there because it doesn't make sense that it would show up in two places, but it does. And then I have to divide out the R and the C to just get the friction coefficient between the journal and the shaft, or the housing in that journal. And so you can use Petrov's equation, which gives you a first pass at it, and then you can use the Sommerfeld number and then the friction number to get a more accurate estimate of what the torque losses, the shear, et cetera, is, right? Okay, so 28 minutes. I hope this is the last time I have to record this video. Now, if I can get it upload to Canvas, we'll be in business, and you guys can get going on the homework. Thanks for listening. Talk to you in a couple days.